Our final topic here in Chapter 5 is trapezoids. It's truly one of the most fun topics in all of elementary Euclidean geometry. And as I said in the previous section, or previous few sections, we now have two tool sets in place, the tool sets of congruence and parallels, and that allows us to prove all sorts of wonderful results, and this certainly is true of trapezoids as well. So let's consider trapezoids. So first of all, we need a definition of trapezoid, of course. And I will say that a trapezoid is a quadrilateral with precisely one pair of parallel sides. Now, you will find, and I was surprised when I first encountered this, you will find that some modern textbooks say that a trapezoid is a quadrilateral with at least one pair of parallel sides. Sorry, misspelled pair. That I say is heresy. Now, usually I'm not one to insist upon a particular definition of a term, but trapezoid has been used in the way that I use it for such a very long time that I honestly just refuse to use it in any other way. Trapezoid has precisely one pair of parallel sides, which means that trapezoids and parallelograms are completely distinct classes of objects. Okay, so a parallelogram does not count as a trapezoid. It sounds insane to me to say that a parallelogram is a variety of trapezoids. So in the diagram you see that we have BC is parallel to AD, and we will assume that AB is not parallel to CD. So we have terminology that goes with trapezoids. We say that the parallel sides are the bases. We say that the non-parallel sides are the legs. So in our diagram, AD and BC, which are parallel, those are the bases. AB and CD, which are not parallel, we call those the legs. And note this is something that we will assume all throughout. It's an obvious result. Perhaps it should be called a theorem, but it's really very obvious. It would be just like a one-step proof. Notice that the parallel sides are not equal in length because one of our parallelogram tests says that if we have a quadrilateral with a pair of opposite sides that are both equal and parallel, it's a parallelogram. So in this case, if BC and AD, which are parallel, if they were also equal in length, this would be a parallelogram, but it's not a parallelogram, so we'll just simply assume that throughout all the work that we do, that the parallel sides in a trapezoid are not equal in length, and as a matter of fact, I give you permission to treat the side that appears shorter as the shorter side. We know that one of the two sides must be the shorter side. It doesn't really matter which one it is. So let's just agree that the side which appears shorter is the one that we will treat as shorter. All right, so all of our results that we will prove concern a particular variety of trapezoid. This is the really fun one, the isosceles trapezoid. And by definition, a trapezoid is isosceles if its legs are equal, as are shown in the diagram. So BC and AD are the parallel sides. AB and CD, the non-parallel sides, that is the legs, are equal in length. So we call it isosceles, which should seem like a good name given how we use isosceles. Now, we'll have properties of isosceles trapezoids in just a moment, and in just a moment we'll also have tests for isosceles trapezoids. So in the properties of isosceles trapezoids, we will be given that a trapezoid is isosceles, and we will prove that it has a certain property, 2 as a matter of fact. And then in the tests, we will be given a quadrilateral, a trapezoid that has a certain property, and we will be able to conclude that it is isosceles. So here, for the properties, in an isosceles trapezoid, angles on the same base have to be equal, and diagonals have to be equal as well. And I want to talk a little bit, I want to talk a little bit about how it is that this could be proven. And I want to suggest a certain strategy to you. There are a number of strategies that could be pursued. That's one of the reasons why trapezoids are so fun. They can be approached in a number of different ways, but I want to show you a beautiful strategy here. So we're given that ABCD is an isosceles trapezoid with AB parallel, AD parallel to BC, and AB equal to CD, as is shown in the diagram. And we wish to prove that angles A and D, a pair of angles on the same base, are equal. Of course, the same strategy could also be used to prove that angles B and C are equal. So we'll just do A and D. Now, here's a strategy, okay? We know that BC and AD are not equal in length. Those are the parallel sides, so they cannot be equal in length. And I said that we will treat the shorter side, the side that appears shorter, as if it is really shorter. So we'll assume that BC is less than AD. So let us do this. So let us extend, okay? It's a construction step. Let us extend BC by the necessary length so that, out to a point E, let's say, so that BE is equal to AD. And these are very familiar construction steps. Extend BC through C so that BE is equal to AD. And then let's think about what we've got, okay? Well, notice now that ABED has, this will be the last bit that I wrote in and the rest of it I'll just talk about. Note that ABED has the wonders of technology, has a pair of sides that are both equal and parallel. That are both equal and parallel. And you know, of course, what that means, right? Thus, it is a parallelogram. Thus, it's a parallelogram. And let's think about what follows from this, okay? Well, here's something that we know to be true. And again, I'll just talk through the rest of this. We know that parallelograms have equal opposite sides, so it follows that AB is equal to DE. Okay, so I've marked that into the diagram. And now consider triangle DCE, okay? It's isosceles. It has a pair of equal sides. And so it follows that its base angles are equal to one another. Okay, so that is the angle DCE is equal to the angle DEC. That's just the isosceles triangle theorem. But now look at CD as a transversal. Look at CD as a transversal for BE and AD. Okay. That gives us alternate interior angles. One of these is DCE, the other is CDA. So we have equal alternate interior angles. So we now have three pairs of equal angles as marked. And then finally, look again at ABED, the parallelogram. We know that parallelograms have equal opposite angles, and in that parallelogram, angles A and E are opposite angles, so they have to be equal. So it now follows that all four of these angles, one at A, one at D, one at C, one at E, they all have to be equal to one another, which means that those base angles at A and D are equal, and the result has been proven. And I often find this to be a fruitful strategy with trapezoids, to introduce parallels or to make parallelograms and then to reason about what we get. All right, now let's talk about the trapezoid test, the isosceles trapezoid tests. In each of these cases, we know to begin with that we have a trapezoid, and we're told that this trapezoid has some additional property, and we will be asked to prove that this trapezoid has to be isosceles. So here's the first. If a trapezoid has a pair of same side base angles that are equal, then it must be isosceles. And second, if a trapezoid has equal diagonals, then it must be isosceles. Now, notice that we are given that the figure is a trapezoid, okay, and then we're told it's a trapezoid with equal, say, diagonals, and we conclude it's isosceles. We're not simply told that, I don't know, this is a quadrilateral, right? I have not said that every quadrilateral with equal diagonals is an isosceles trapezoid. We must begin with the trapezoid. I say this because I've seen the mistake before. So here we go. We have trapezoid ABCD with AD parallel to BC. And we're given that the diagonals AC and BD are equal. And we wish to prove that ABCD is isosceles. Now, as for a strategy, I almost hesitate to show you this. I would sometimes think that I should let students just struggle to find the beautiful proofs. But sometimes I think you should be shown beautiful strategies to prove results, and I'm going to do that in this case. And in this case, it starts with the construction of a parallel. So let us, through point D, I'll write this out, through D, construct a line parallel to AC. Okay, so let us do this. So through D, construct a line parallel to AC. I'll try to make this look halfway decent. And then let us extend BC. I'll tell you what, I'm going to erase this out because it's going to be a bit of a mess. I'll just talk through it. You'll be able to follow, I'm sure. So let me just talk through this. Through D, construct a line parallel to AC, and then extend BC out to the point of intersection with this construction, and we'll say that they intersect at point E. Okay, and you might consider for a moment how you know that these will intersect with one another. It's not very difficult to prove. But again, what we've done is this. We have constructed a line through D so that it is parallel, better use 2, so that it is parallel to AC. And then we extended BC through C until the point E where it intersects that line that we introduced. Okay, and then let's consider what we've got. ACED, I'll say that again, ACED is a parallelogram. Okay, we know that CE is parallel to AD because CE is just simply the straight extension of BC, and BC was parallel to AD. And DE, just by construction, is parallel to AC. So this is a parallelogram. Okay, and parallelograms have equal opposite sides. So it follows that AC is equal to DE. And now, and I know there's some complexity here, but follow me. And now consider triangle BDE. Triangle BDE. It has a pair of equal sides. This means that it's isosceles. And this means then, of course, that its base angles are equal to one another. So its base angles, as I'm about to mark, are equal to one another. That is, angle DBE is equal to angle DEB. Okay, DBE is equal to DEB. The base angles of this must be equal to one another. But now, let's consider a pair of alternate interior angles. Okay, where BD will be our transversal. So it's lines BE and AD with transversal BD. Angles DBE and BDA are alternate interior, so they must be equal to one another. So we now have a third angle in this set of equal angles. And then finally, very much like what we did in the previous proof, we know that parallelograms have equal opposite angles, and ACED is a parallelogram. So we know that the angle at A in that parallelogram is equal to the angle at E. So all 4 of these angles now belong to the set of equal angles. And then finally, consider triangles. There are various ways to finish this out, but here's one way. Consider triangles BDA and CAD. Again, consider triangles BDA and CAD. AC in one is equal to BD in the other. The angle in A in one is equal to the angle C in the other. And of course, they share side AD in common. So those triangles are congruent by side angle side. And it follows that the third pair of sides in these two congruent triangles are equal. And the third pair of sides are AB and CD. So it follows that AB is equal to CD by CPCTE. And I find that to be an absolutely extraordinary proof. Of some complexity, it's perhaps one of the most complex proofs that we've considered together, but it's a wonderful example of how it is the machinery of congruence and parallels can work together to prove new results. All right, finally, the final set of results that I wish to consider, and one of these we've already encountered. We'll actually come back to it again at a later point as well. It's about mid-segments. Okay. We'll consider mid-segments both in triangles and trapezoids. And what mid-segments do is they connect midpoints. In a triangle, they connect the midpoints of a pair of sides. In a trapezoid, they connect the midpoints of the legs specifically. So here are diagrams to illustrate the idea. On the left-hand side, we had triangle ABC, and then D and E are the midpoints of 2 sides, which makes DE a mid-segment. And then we also have trapezoid A, B, C, D. E and F are the midpoints of the legs, which were connected together to create the midsegment EF. And you'll prove some results about these. And we'll also find that these results will be very significant to us later on in the second semester when we discuss similarity. But we can already prove them, so we'll prove them. The first is the triangle midsegment theorem, the TMT, which says this. It says that the midsegment is parallel to the base. That is, in this case, DE is parallel to AC, and it's also half the length of the base. Now, I won't consider the proof of this with you here. Instead, I guide you through that proof on the worksheet. It involves multiple constructions. But do know this, when we get to the second semester in our study of similarity, the proof will be dramatically simplified. And this is often the case, that difficult proofs become simpler once more machinery is in place, once you have more tools. We already saw this in the case of the converse ITT. Our first proof of converse ITT way back in the chapter on congruence was fairly complex. It was by contradiction. Perhaps you don't remember, but it was complex. And then once we had proven the triangle angle sum theorem, which then gave us angle side congruence, the proof of converse ITT became much simpler. And this is just typical in mathematics. Sometimes you can prove a result at a certain point in the development of a mathematical system, but it's quite difficult. Later on, however, once that system has been extended, once you have more tools in place, the proof of the result becomes much simpler. All right, and finally, let me mention what you'll prove with the trapezoid midsegment theorem. You'll prove, first of all, that that midsegment is parallel to the basis. So in this case, you'll prove that EF is parallel to both AD and BC. Of course, if it's parallel to one, it's parallel to the other. That's the transitivity of the parallel relation. And you'll also prove that it's half the sum of the lengths of the basis. You'll prove that EF is half the sum of AD and BC. And as for how you prove this, it's really quite an extraordinary proof. There is a way to turn this into the triangle midsegment theorem. And on the problem set, the exercise set for the section, I'll show you a set of constructions that will bring the triangle midsegment theorem into play, which is also something very characteristic of mathematics. Very often a way a new problem gets solved in mathematics is you turn it into an instance of an old problem. So this will be turned into an instance of the triangle midsegment theorem, or at least the crucial move in the proof will be provided by the triangle midsegment theorem.